Now, till now we have covered the Laplace transform, the properties of Laplace transform, how to find out the Laplace transform of various functions, various properties, convolution. Similarly, after that we have gone through the Fourier transform, Fourier sine transform, Fourier cosine transform and their properties, and we are finding the how to find out the Fourier transform or Fourier cosine or sine transform of various functions and how to use their properties. Now, let us come to the third topics, that is the application of this Fourier and Laplace transform on the partial differential equations. If you remember, whenever we are doing the Laplace transform, during the Laplace transform we have seen that how to find out the solution of ODE using the Laplace transform by converting it in simple algebraic equation. That is, the ODE was converted into the simple algebraic equation, and by solving the algebraic equation we were finding the solution of the ODE. So, now let us see in the how to find out the solution of partial differential equation using these Laplace and Fourier transforms. So, before going to the application of this, let me very briefly talk about the partial differential equation first, and then we will go through the other part. So, let us see the partial differential equation. You all may be knowing, just I am brushing up this one. An equation which involves the partial derivatives with respect to more than one independent variables, we call it as a partial differential equation. So, please note that I have a equation which involves the partial derivatives, and the partial derivatives are with respect to more than one independent variables, then we call it as PDE or partial differential equation. Whenever we talk about the differential equation, we always try to talk about two things. One is the order, another one is the degree. The order of a differential equation is the order of the highest derivative involved in the differential equation. Please note this one. The order of a differential equation is the order of the highest derivative involved in the differential equation. I will give example just after this. So, whatever highest derivative is there, that we call as the order of that differential equation. And what is degree? The degree of a differential equation is the power of the highest order derivative involved in the equation, when the equation has been made rational and integral as far the derivatives are concerned. So, again I am repeating it, the degree of a differential equation is the power of the highest order derivative. Please note that this is the order of the highest order derivative which involved in the equation, that is the degree, and the order is the highest derivative, whatever is there, that we call as the order. So, let us see some examples. So, let me just make it like this. I will show you the slide also. Some equation we will write down, and we will try to find out what will be the order and what will be the degree of that particular equation. So, suppose you have an equation d2y dx square, this is equals to ky. From the definition, what we have told, that what is the order? Order is the highest order derivative which appears in the equation. Here the highest order derivative is second, that is d2y dx square. Therefore, the order of this equation will be 1. And what is the degree of this highest order derivative? Degree is 1, no whole square or like that is involved. Therefore, for this the degree will be equals to 1. So, please note that d2y dx square equals ky. here the order is the highest order derivative. The second order derivative appears here, that is the highest order. Therefore, order of this equation will be 2 and the degree of this equation will be equals to 1. Similarly, say we have an equation dy dx whole square equals 4 into dy dx minus 2y square. So, equation is dy dx whole square equals 4 into dy dx minus 2y square. So, what is the highest order derivative is appearing, that is first order, only dy dx. Therefore, order of this is 1 and what will be the degree? Degree is the degree of the highest order. Your highest order derivative is dy dx and whole square is there. Therefore, your degree will be equals to 2. So, for this equation the order is 1, the degree is 2. You see this one del 2v del t square, this is equals to k into del cube v del t cube whole square. So, here what is the highest order appearing, that is third order, because you have del 2v del t square, you have del 3v del t cube, sorry del cube v into del t cube. So, the order of this equation will be 3, whereas the degree will be, what is the degree of the highest order? Degree of the highest order is 2. So, therefore, it is equals to 2. So, we are writing that for this equation the order is 3, but the degree is 2. Similarly, if I take this equation d2y dx square to the power say 3 by 2, this is equals to a into d2y dx square. If I have an equation like this, in this case what you are finding that what is the highest order derivative appears here? The highest order is d2y dx square, that is second order. Therefore, the order would be 2 and what is the degree? Degree is equals to, here it will be 3, because if I wish I can multiply both side by whole square. So, that this by 2 will be cancelled, this side there will be whole square on the right hand side and on the left hand side there will be cube if I make whole square on both side. Therefore, degree of this equation will be 3. So, like this way we find out the order and degree of a partial differential equation. I think that it is now clear to you that how we find out the degree and the order and degree of an equation. So, just those things in a tabular chart again I am showing you what I have explained. So, the order and degree. So, I hope it is clear to you now. So, let us proceed to the next one, linear and nonlinear differential equation. When one differential equation we will call as linear differential equation and when we will call it as nonlinear differential equation. A differential equation is known as linear or is called linear if number 1, every dependent variable and every derivative involved occurs in the first degree only. You please note this one, every dependent variable and every derivative involved occurs in the first degree only. Number 2 is no products of dependent variables and slash or derivatives occur. No product of dependent variable and or derivatives occur. So, here one example we are writing x square into d2y dx square, this is equals to ky, this is the linear form, whereas a nonlinear differential equation is defined as a differential equation which is not linear, obviously will be known as the nonlinear equation. So, an example we can give as del 2 v del t square equals k into del cube v del t cube whole square. Please see this one that we have used the whole square here, therefore, it becomes nonlinear. So, therefore, if the partial derivatives and the dependent variables, if they occur in the first degree only, then we call it as the linear, otherwise it is nonlinear. So, to check whether it is linear or nonlinear, it is always desirable that your concept on the degree and the mode is totally clear. Otherwise, it will be difficult for you to judge whether an equation is linear or nonlinear. Now, a linear PDE of second order, linear PDE of second order with two independent variables in general form, we write it as del 2 u a into del 2 u del x square plus b into del 2 u del x del y plus c into del 2 u del y square plus d into del u del x plus e into del u del y plus some function of u, that is, I can write it, it is a function of x y u del u del x del u del y. This is equals to g of x y say. So, this is a linear PDE of second order of two independent variables x and y. So, effectively it is given that u is a function of two independent variables, and a second order linear PDE with two independent variables, we write it, the general form is a into del u del x square plus b into del u del 2 u del x del y plus c into del 2 u del y square plus d into del u del x plus e into del u del y plus function of x y u del u del x del u del y equals g of x y, where obviously a, b and c cannot be all 0. Please note this one. If all these three are 0, then it will not be a second order, because all second order derivatives are being vanishing. Whenever I have this general equation, then I can make the classification of this general equation depending upon the value of this a, b and c. So, depending upon that value, once I am making the classification, I am not going to how to classify it, because for that we have to go through the course of PDE. Just we are giving an introduction to PDE to know. Number one, we say that this equation we call it as elliptic equation if b square minus 4 ac less than 0. Number 2 is hyperbolic if b square minus 4 ac equals to 0, and is parabolic if b square minus 4 ac, hyperbolic if b square minus 4 ac greater than 0, and parabolic if b square minus 4 ac this is equals to 0. So, these are the three classifications basically we have. The second order linear PDE can be of elliptic, hyperbolic or parabolic depending upon the value of b square minus 4 ac. If b square minus 4 ac is less than 0, it will be elliptic. If b square minus 4ac greater than 0, it is hyperbolic, and if b square minus 4ac equals 0, we call it as parabolic. So, just let us see this one once we are doing it. So, the general order second order equation, we are writing this f of u I have written capital F of u, that is nothing but a function of x, y, u, del u del x and del u del y, and a, b, c cannot be all 0. So, it is elliptic if not b square minus 4ac. Similarly, it will be b square minus 4ac greater than 0, and so it is elliptic if b square minus 4ac less than 0, which we call as Laplace equation, is hyperbolic if b square minus 4ac is basically greater than 0, and it is an b square parabolic if b square minus 4ac equals 0, which we call as the heat equation. Let me little bit explain these terms as what is the wave equation. First, let me come to the wave equation. We have an elastic string. Please note that this is your elastic string is there, and we have fixed it at 2 points, this point and this point, and at t equals 0, at any time t equals 0, suppose the string is released, we are releasing the string and we allow it to vibrate. So, a string is there at any point of time, that means at this position, at any point t equals 0, we are allowing this string, we are releasing the string and we are allowing it to vibrate. So, if the vibration is uxt at any time t, at any point x and for any time t greater than 0, then the wave function can be defined by an equation which we call as wave equation. So, basically you have a string which is fixed at 2 points. At any time t equals 0, you are releasing the string and you are allowing it to vibrate. Automatically it will vibrate if the string you allow to, you release it, then it will vibrate. So, to measure the vibration, basically we use the wave equation. So, what you are doing, the deflection, whatever deflection you will obtain, this deflection we call it as uxt. This deflection uxt, you can measure it at any point x, at any point x and at any time t greater than 0. This deflection can be measured by uxt and by the equation which we call as this one, del to u del t square equals c square into del to u del x square. This is one, where your c square equals capital T by s, this I am not explaining now. So, this is c square equals T by s. This we call that one dimensional wave equation. This one we call it as one dimensional wave equation. Okay. So, whenever you have the string, you are allowing it, you are releasing it and allowing it to vibrate, then the deflection can be measured at any point uxt, where for any point x and any point time t greater than 0 by this equation, and this equation del to u del t square equals c square into del to u del x square, where c square equals T by s. This we call as one dimensional wave equation. Similarly, it can be measured by del to u del t square equals c square into del to u del x square plus del to u del y square. This is known to us. This we call as two dimensional wave equation. Please note this one. There was only the variables was x and t, here it is x, y and t. So, one dimensional, this is two dimensional wave equation. So, your del 2 u del t square equals c square into del 2 u del x square plus del 2 u del y square. This we call as two dimensional wave equation. First one is the one dimensional wave equation. I am not coming how the wave equation has been derived, because then we have to go at length at the other places. So, that we will not do, just we are defining the equation, so that you are familiar with the equation. So, the string is there which is fixed at 2 points. Now, you are taking the string at a particular position at a time t equals 0. You are releasing it, you are allowing it to vibrate. Whenever it is vibrating, the deflection of the string can be measured by a equation, and the function we define it as u x t, and that can be measured by the equation del 2 u del t square equals c square del 2 u del x square, where c square equals t by s. This we call as one dimensional wave equation, and similarly del 2 u del t square equals c square into del 2 u del x square plus del 2 u del y square. This we call as two dimensional wave equation. So, the equation of the form del 2 u del t square equals c square into del 2 u del x square is the one dimensional wave equation, and del 2 u del t square equals c square into del 2 u del x square plus del 2 u del y square, we call it as two dimensional wave equation. As I told you, mainly we work with three type of equations: parabolic, hyperbolic and elliptic. So, one is the wave equation. The next one is the heat equation. Thermal energy is transferred from warmer to colder regions interior to a solid body by conduction. So, basically energy is being transmitted from one place to another place, we can think. Then, if u is the temperature at any time t, the heat equation can be written as this one. One dimensional heat equation, we write it as del u del t equals c square into del 2 u del x square. Please note this thing. One dimensional heat equation can be written as del u del t equals c square into del 2 u del x square. Similarly, two dimensional heat equation can be written as del u del t equals c square into del 2 u del x square plus del 2 u del y square. So, please note this, the two dimensional heat equation equals del 2 u del t equals c square into del 2 u del x square plus del 2 u del y square. Similarly, three dimensional heat equation also we can define as del u del t equals c square into del 2 u del x square plus del 2 u del y square plus del 2 u del z square equals c square into del square u. So, capital del square u is nothing but del square u del x square plus del square u del y square and del square u del x square. So, this is the second one. First one we discussed this one. The first one was wave equation, where you are measuring the deflection of a string. In heat equation, you are basically measuring the temperature, whichever energy is transferred from one region to another region. For that, you have three type of heat equation: one dimensional, two dimensional and three dimensional, and the third one is the Laplace equation. When the temperature is in steady state, that is, the u does not vary with time, then the heat equation is known as Laplace equation. Please note this. When the temperature is in steady state, that is, the function u does not vary with time. In heat equation, u function of t is varies with time, but in Laplace equation, u does not vary with time. Then we say that del 2 u del x square plus del 2 u del y square plus del 2 u del z square, this is equals to 0. And this means basically as I told you del square u this is equals to 0. So, this equation we call it as Laplace equation. So, these three type of equations, now if you see the heat equation, wave equation, heat equation and the Laplace equation. So, in one form if I have to write, I will tell the heat equation is of the form like this. In one place I am writing, sorry, not heat equation, first let me write down wave equation del 2 u del t square equals c square del 2 u del x square, you can write it, or you can write it del 2 u del t square equals c square into del 2 u del x square plus del 2 u del y square, where your c square is t by capital T by s. Then your heat equation, I am just writing the heat equation. Your heat equation takes the form del u del t equals c square into del 2 u del x square, or you can write down del u del t equals c square into del 2 u del x square plus del 2 u del y square, or you can write down del u del t equals c square into del 2 u del x square plus del 2 u del y square plus del 2 u del z square. This you can write down as c square into del square u. And the last one is Laplace equation. And Laplace equation, as I told you, the temperature is in steady state, that is u x t does not vary with time, then we can write it as del 2 u del x square plus del 2 u del y square plus del 2 u del z square. This is equals to 0, or which you can write down del square u this is equals 0. So, basically whenever any second order PD is there, linear PD is given, we can classify into either parabolic or hyperbolic or elliptic, and these three are corresponding to the wave equation, heat equation and Laplace equation. And our basic aim will be how to find out the solution of this type of equations using the Laplace transform and Fourier transform. This is our basic aim, and in the subsequent lectures we will see how we can find out the solution of this.